Hi everyone, this is the second in a series of 3 videos covering the content for differential calculus topic for the International Baccalaureate course Maths Standard. In this video we're going to go through the chain rule, product rule, quotient rule. Then we'll look at how we differentiate exponentials, logarithms and trigonometric functions, and we're going to finish off with higher derivatives. So here's a question: differentiate y is equal to, and then in brackets 2x minus 1 all squared. Now currently our only option is to expand and then differentiate. So we expand it, we're going to get 2 squared, 2x all squared, which is 4x squared, minus 2 times 1 times 2x, which is 4x, and then plus 1 squared, which is 1. And then we would want to differentiate, so 2 comes down, we're going to get 8x minus 4. But this is going to prove difficult if we're asked a question like this, for instance, where these powers start creeping up. We could do it, but the chance of error increases. So here's the first of our 3 rules that we're going to learn. It's called the chain rule. It's also known as function of a function rule. And we use this when we have a function embedded or inside another function. So there's our first question, y equals 2x minus 1 all squared. Can you see how we've got 2x minus 1 inside another function? So we've sort of got a y equals something squared, and then inside the something we've got 2x minus 1. So that's a function in a function. Up here is the chain rule as it's presented for you on the formula sheet. I don't really use the formula, so I'm going to show you a different way of doing it, but it is there. It can come in handy with some other types of questions, which we'll do later on. So recall, if f of x is equal to x squared and g of x is equal to 2x minus 1, let's write f of g of x. Do you remember this? So f of g of x is actually written like that, or can be written like that, where we put the g of x inside the f of x. Can you see where I'm going with this? So it's 2x minus 1 all squared. It's a function inside another function. So the chain rule is actually used for composite functions. Okay, so let's return to this question. Differentiate y equals, in brackets, 2x minus 1 all squared, and let's do it by the chain rule. So what we're going to do is ignore this in here and differentiate this as if we didn't know what it was. So the 2 is going to come down, we'll just write that out blindly, and then it's going to be to the power of 1. There it is there, that's to the power of 1. And then we're going to multiply by the derivative of the second function, or the internal function, because the derivative of this is 2. And you can sort of see where that's happening here. So we're taking y and differentiating it with respect to some other variable, and then multiplying by the derivative of the other variable. Okay, so that's where that formula comes from. Now all we've got to do is tidy that up, and that's of course going to give us 4, and then in brackets 2x minus 1, which is identical to what we got before. All right, now here's this hard one that we really were going to struggle to expand out. So when we differentiate, the 7 is going to come down. Leave this as it is, we don't care what's going on in there, and drop this power by 1, and then times by the derivative of what's in the brackets. So I'm going to get 7, and in brackets 2x minus 1 all to the power of 6 times 2, and I can bring that 2 out the front. It's going to give me 14, and then in brackets 2x minus 1 all to the power of 6. So the chain rule is really easy to do. Here's a harder one. Here I've got square root of 1 minus x squared, and just like we've been doing before, I need to change that into index form. And again, I have a function sitting in another function. So when I do my derivative, I'm going to do the outer function first, bring this half down, leave that alone. That's going to become to the negative half. Multiply by the derivative of the internal function. Let's have a look at it. A half, 1 minus x squared, all in brackets, to the power of negative a half, times by derivative of this is negative 2x. Okay, we can cancel those 2's out, and to tidy it up, all I've got to do is bring this x out the front like that. And that's actually the answer. We could bring this down onto the denominator if we wanted to, but it's not necessary. Moving on to our second rule, the product rule. Suppose we had a question like this: differentiate y equals, and in brackets 2x minus 1, second bracket x squared plus 2. Currently all we can do there is expand it out and then differentiate term by term. It's different than the chain rule. Can you see that? Because I've just got two different functions multiplied together. And that's actually why it's called the product rule. Let's do it the old way. Expand it out just using FOIL. We're going to get 2x cubed plus 4x minus x squared minus 2. Differentiate term by term. I get 6x squared plus 4 minus 2x. Now, this is the product rule. If I've got a function that's obviously two separate functions multiplied together, then dy dx, or the derivative, is going to be equal to the first function multiplied by the derivative of the second function plus the second function multiplied by the derivative of the first function. So back to our question, y equals 2x minus 1 in brackets x squared plus 2 in brackets. So this is u here, and this is v. You can set it out formally and do the derivatives and then construct the formula. I'm going to show you how easy it is just to write it down. But then later on, the more complicated the questions get, sometimes I will do it more formally. So you can choose your method, basically. So our derivative is going to be the first one multiplied by the derivative of the second, plus the second one multiplied by the derivative of the first. Okay, so that's our first line. Now I'm going to expand that out and tidy it up. And we get the same answer, not surprisingly, as when we expanded it and did it term by term. All right, we can combine the two rules. Now let's have a look at this. We've got a product. See, I've got a 2x multiplied by another thing. And this second thing, the v here, has got a function in a function. Now in this case, I am going to set it up formally. So I'm going to let u equal 2x and let v equal x squared minus 1 all to the power of 5. And now we're just going to differentiate both of those. That's easy there. This one, the 5 comes down, leave this alone to the power of 4, multiplied by the derivative of what's in the brackets, which is 2x. And take the time to tidy this up. So I'm going to bring that 2x out the front, so 10x, and then x squared minus 1 all to the power of 4. All right, now we can construct our rule. So y dash is going to be u dv dx, see how that's there, plus v du dx. Now, we can just tidy that up and leave it there like that. That's perfectly fine, and you'll get all the marks at that point. We can factorize it though. I'm going to show you how to factorize it. If this is too far for you, that's all right. Just ignore it and fast forward. But I've got a common factor here of 2 and also x squared minus 1 all to the power of 4. So I'm going to bring that out the front. Okay, once I've brought that out of the front of this term, I'm left with 10x squared plus the 2's already come out and 4 of those have come out. So that's just going to leave me with 1 left. And the last thing I'm going to do is just tidy that up and make that 11x squared. And that's it. Here's another one. Again, we've got a product, and this one here is a chain rule because I've got a function inside another function. So let u equal 2x minus 1 and v is equal to that, which I have to put in index form. Do the derivative. So the derivative here is nice and easy, it's 2. Here, the half comes down, leave that alone, drop this power by 1, so that's negative a half, multiplied by the derivative of the thing in the brackets, which is 2x. Just like before, those 2's are going to cancel out, which is nice. And we're going to be left with x outside of x squared minus 3 all to the power of negative a half. Okay, don't stop here. We've still got to construct the rule. So y dash will be u, don't forget to put that in brackets. That's a really common error, by the way. So u dv, see how I've just written it there, plus v du. Now again, we can just bring this x out the front and this 2 out the front here and leave it like that. That's fine. If you want to go further, I'm going to further simplify it on the next page. You can ignore it if you want to. So from here, what we're going to do is change these back to square roots. That's just going to be the square root of x squared minus 3. This one's going to be 1 on the square root of x squared minus 3, like this. Could leave it like that, but let's make a common denominator. So I'm going to make that denominator here x squared minus 3. And of course, whatever I do to the bottom of a fraction, I've got to do the top. And I'm effectively actually squaring this top because I'm multiplying it by itself. Now, of course, square and square root are opposite operations. They cancel each other out. And so when I rewrite this, I'm going to get, I've just expanded this here, 2x squared minus x plus 2, and you can see how the square root's gone. And then the final thing is just to tidy up that numerator. Okay, the third of our rules is called the quotient rule, and we use the quotient rule whenever we have a function divided by another function. So here's the rule. So if f of x is some function divided by another function, then the derivative will be v multiplied by du dx minus u multiplied by dv dx, all divided by the denominator squared. Okay, so here's a quotient rule. So we've definitely got a numerator, a function on the numerator, and a function on the denominator. So this is u, and this is v. Do the derivatives. So u dash will be 2x, v dash will be negative 2. Okay, now we've got to construct that quotient rule. Here it is here. So it starts off with v. Don't forget to put him in brackets. V times du dx minus u, he needs to be in brackets too, u multiplied by dv dx, all divided by this denominator, or v squared. Now tidy up the numerator and we're pretty much done. So we're going to get 2x minus 4x squared plus 2x squared, and I've got a minus and a plus there, so that makes a plus 10. And then just a bit of tidying up to do here. Minus 2x squared plus 2x plus 10 all over 1 minus 2x all squared. So it is a little bit more complicated, the quotient rule. Common error is to just forget about the denominator. So just doing the numerator. So make sure that you have the formula sheet with you and you follow it religiously. So here's another question. This time I've got a quotient rule with a chain rule sitting in there. Don't know if you've seen this notation before. This means find the derivative of this. It's a shorthand way of writing it. So this effectively is y, and it's replaced the dy dx. So it still means find the derivative. Okay, we're going to start off with making u equal x and v equaling the square root of 2x minus 1. And I've already just changed that sneakily to 2x plus 1 to the power of a half. Do the derivatives. That's derivative of 1 here. The half comes down. Leave this alone to the negative a half, multiplied by the derivative of what's in the brackets, which is 2. They cancel out. And I'm left with 2x plus 1, all in brackets to the power of negative a half. Now put it in the quotient rule. So d dx of x all over the square root of 2x plus 1 is equal to v, that's there, times du dx minus u multiplied by dv dx, all over the denominator squared, which of course will cancel out that square root there. So 2x plus 1 on the bottom. And all I'm going to do with this to tidy it up is get rid of this 1 and take out that times symbol there. You could further simplify it, but I'm choosing not to. Okay, we're going to move on to differentiating exponentials. And we're going to start with this question. What function remains the same when differentiated? Now this is a common thing for mathematicians. As soon as they discover something, firstly they want to know if they can do it backwards or reverse it, and we will be reversing differentiation in another topic. And then the next thing they want to know is there a function that when we do this thing to it, it remains unchanged? And there is a function that when we differentiate it, we get the same function. It's called e to the x. We're going to have a look at y, and we're going to start with the derivative of 2 to the x, which is not pretty. We have to do it from first principles, which you've probably tried to avoid. So this says d dx of 2 to the x is equal to the limit as h approaches 0 of f of x plus h, so I've just put the x plus h in there, minus f of x divided by h. Okay, so we are going to split this up into 2 to the x times 2 to the h, and actually then we'll have a common factor of 2 to the x, which I've brought out the front. Now because this 2 to the x doesn't have an h in it, it's not affected by this, it can come out the front. And so I've got 2 to the x times this limit thing, and I can't go any further. H won't divide into that, so I'm stuck. Now before we move on to e to the x, let's have a look at the derivative of 3 to the x. It's actually identical, except it's got 3's in it. So here we've got 2 to the x times something or other, and here we've got 3 to the x times something or other. We're going to now try and figure out what this something is equal to. Now because we can't get an exact value for this, we're just going to set up a table and make h get smaller and smaller, tend towards 0, and see if we can figure out what this is approaching. So this looks like it's sort of leveling out around 0.69. It's getting closer and closer to that point. This one heads down, 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 and sort of starts to level out about 1.09 something. So the limit as h approaches 0 of 2 to the h minus 1 divided by h seems to approach 0.69. And the limit as h approaches 0 of 3 to the h minus 1 divided by h seems to approach 1.09. In other words, the derivative of 2 to the x is slightly under 2 to the x. Remember this thing here was multiplied by 2 to the x? So it's slightly less than itself. And the derivative of 3 to the x is slightly above itself. So we would assume that somewhere between 2 and 3 there exists a function, or one of these exponentials, where the derivative is itself. And there is. There exists a number denoted by e, for which the derivative is e to the x itself. E is called the natural number, or Euler's number. And you could check this out on a calculator, put in a really small value for h, and you'll see that it starts to approach 1. So 1 multiplied by e to the x is e to the x. Now on the calculator, you'll find it above the ln button, or looks like in e to the x. You'll have to put a 1 in where the x is to get its value. It's approximately equal to 2.718281883, etc. And just like pi, e is irrational, which means it never ends and never repeats, and it's transcendental, which means you can't get it from solving an equation, which of course makes our life pretty easy. What's the derivative of e to the x? It is e to the x. They're not going to give you that question, by the way. What about this one? E to the 3x. That's a chain rule. Okay, I've got a function sitting in a function. So what do I do here is I'm going to do the derivative of that, which is that, and then multiply by the derivative of the second function, which is going to be 3. And so our answer there's going to be 3e to the 3x. Okay, here we have a product rule. Can you see why it's a product? It's two things multiplied together. I've got u and v, and this one here is also a chain rule. So let's write it out. Let u equal x squared, let v equal e to the 3x plus 1. Differentiate, we get 2x. Differentiate here, I leave that the same. Multiply by the derivative of the second function, which is 3, tidy it up. Okay, don't stop there, we actually haven't done anything yet. We need to construct the product rule. So product rule says u multiplied by dv dx plus v multiplied by du dx. Now when we want to tidy this up, we could just do 3x squared e to the 3x plus 1 plus 2x e to the 3x plus 1, but we do have a lot of common factors there. So let's bring an x out of this and this e to the 3x plus 1 out the front. So if I've taken x and e to the 3x plus 1 out there, I'm left with 3 and an x plus, I've taken that, I'm left with 2. So there's our answer. Again, if you just tidied that up and brought the 3 out the front and the 2x out the front, you'd actually get that completely correct. Okay, we're moving on to logarithms. Now, think about the function y equals x to the power of n and its derivative. Y equals, bring the n down, x to the power of n minus 1. There's one derivative, y dash equals nx to the n minus 1, that we can't get from a function of this form, y equals x to the n. I don't know if you've thought of this before. There's one that won't happen, and it's this one. Have a think about why that might be. So x to the negative 1. So if I want this thing here to be negative 1, then n would be 0. What happens if I have a 0 here? 0 times anything is 0. So we actually can't get this. And you may have seen this, like if we start with y equals x squared, and we do the derivative, and we do the derivative again. At this point, at the third derivative, we get 0, and any subsequent derivative will also be 0. Because the 0 is wiping it out, it's stopping us getting negative powers. So we're going to use logarithms for this. So let's consider the function y equals log base e of x. There's our friend e again. I'm going to turn that around and make that e to the y equals x. Okay, so I've just turned it into index form, and I actually turn it around. Now I'm going to do dx dy. Okay, I know you're used to doing dy dx, but we can differentiate any variable with respect to another one. So I'm going to do dx dy like that. And of course I am just differentiating e, and e remains the same. Fair enough? Okay, the next thing I'm going to do is flip this upside down, both sides, take the inverse of both sides. So dy dx, because that's really what I want, is going to be equal to 1 on e to the y. What's e to the y? It's x. Alright, the derivative of log base e of x is 1 on x, or x to the negative 1. It's our missing function. So let's find the derivative of ln 2x. You can see here we've got a function inside another function. So I'm going to do this outer function first. So that's going to be 1 over 2x. And then I'm going to times by the derivative of the second function, which is 2. And those 2's are going to cancel out, and we're going to be left with 1 on x. Now, does this strike you as curious? It's the same derivative as ln x. And in fact, if we had ln 3x, we'd get the same thing. 1 over 3x times 3 equals 1 over x. And if we remember our log laws, it actually makes sense. So have a look at log 2x. When we've got a product, we can separate them out, can't we? So this is going to be ln 2 plus ln x. All right, what happens when we differentiate this? This is just a number. What happens when you differentiate just a number? 0. So it's going to end up being just the derivative of ln x, and that's why with any of these ones it's just going to end up being 1 over x. Here's another one. This time we've got a product rule, and in both of them we've got a second function. So we've got a chain rule here and another chain rule. This one's going to be u and this one's going to be v. Alright, rather than write out u equals and v equals and do the derivatives, I'm going to actually put it straight into the product rule. Let's see if you can follow this. So I'm going to write the first one down, e to the 2x multiplied by the derivative of this. That's going to be 1 on x squared plus 1 multiplied by the derivative of the second function. So there's the first bit. E to the 2x multiplied by, there's the 1 on x squared plus 1, and then multiplied by the derivative of that, plus, write down the second one, multiplied by the derivative of this, which is 2e to the 2x. So there's the ln x squared plus 1 multiplied by e to the 2x times the derivative of the second function, which is 2. Okay, tidying that all up, I get this, and I'm actually going to leave it like that. So you can get confident enough to put it straight into the formula, but if you are hesitant at all, separate it out and write u equals e to the 2x and v equals ln x squared plus 1 and do it that way. Here's another one. Differentiate log base e of x cubed all over x to the 4. So we've got a quotient rule now. This is u, this is v. Derivative of this. So log base e is going to be 1 over x cubed multiplied by the derivative of the second function, which is 3x squared. And when I tidy that up, I can cancel out the x squared and the x cubed here. So I'm going to be left with 3 on x. And here, derivative of that is 4x cubed. Right, let's construct our quotient rule. So it's going to be v multiplied by du dx minus u multiplied by dv dx all over the denominator squared. A couple of things I can tidy up. That x will cancel into this x to the 4 and become x cubed, like that. X to the 4 all squared is x to the 8. Actually, that's going to be able to be cancelled here. So I will cancel that out. I could have factorised that. You could do that if you wanted to, but I've just taken x cubed out of here and cancelled it with that and that. I probably would do it like this if I was doing it in a test. Okay, and that would be sufficient. There's our answer. So now we're up to differentiating trig functions. You have the following derivatives given for you on the formula sheet. So the derivative of sine is cos, the derivative of cos is negative sine, and the derivative of tan is 1 over cos squared x. And we can use chain rule, product rule, and quotient rule with all of these as well. So let's find the derivative of sine 2x. Here's a chain rule. We have a function 2x sitting in another function. So it's going to be differentiate the outer function. Sine 2x will become cos 2x, multiplied by the derivative of the second function, which is 2. Bring the 2 out the front. 2 cos 2x. Nice and easy. About this one, here is a product rule. 3x multiplied by cos x. So u is 3x, cos x is v. Differentiate both of them. Derivative of 3x is 3, derivative of cos x is negative sine x. Construct the product rule. U multiplied by dv dx plus v multiplied by du dx. Tidy it up. Here's another one. Find the derivative of y equals the square root of cos x. Now this time we've got cos x as the internal function inside a square root. But that's okay. We're going to turn this around and put it in index form. So cos x all to the power of a half. Okay, we're going to bring the half down, then cos x to the power of negative half multiplied by the derivative of the second function, which is going to be negative sine x. Tidying that up, bring this negative sine x out the front. You could take the cos x down underneath if you wanted to and do the square root, but that's fine the way we've left it, like that. Okay, the derivative of tan x. Now, I've already discussed that that's equal to 1 on cos squared x, but I'm going to actually prove it. Recall that tan x is equal to sine x on cos x, so it's actually a quotient rule where u is sine x and v is cos x. Do the derivatives, so u dash will be cos x and v dash will be negative sine x. let's construct the quotient rule. So d dx of tan x will equal v times du dx minus u times dv dx, all divided by cos x all squared. So this is cos x all squared, and then I've got plus sine x all squared. Now, just a note here. Cos x all squared can be written as cos squared x. It's a shorthand way of writing it, but it's not equal to cos x squared. Okay, so they're kind of taking liberties writing it like this, because it really is cos x times cos x, but this has become accepted notation. Okay, that's completely different. That means cos of x squared. So here you can see I've got cos x all squared. I've turned it around to be cos squared x, and same here, cos x times cos x is cos squared x, and sine squared. What's this numerator equal to? Sine squared x plus cos squared x equals 1. So there's our answer. Here's another one. Find the derivative of y equals e to the 2x divided by 3 sine x. So u will be e to the 2x and v will be 3 sine x. Derivatives. Now, I've done this one straight in one line because you start to get very familiar with it. E to the 2x, I do the derivative and it becomes e to the 2x, and then multiply by the derivative of the second function, which is 2, and bring it out the front. Derivative of 3 sine x is 3 cos x. Construct the quotient rule. So I'm going to get v times u dash minus u times v dash divided by v squared, which is 9 sine squared x. Let's bring out a common factor. We've got a 3 here, and we've got an e to the 2x. And that's going to leave 2 sine x there minus cos x here. And that's as simple as it's going to get. Oh, no, it's not. I can cancel this out. So 3 into 9 goes 3 times. So there's our answer. How do we know when to use the chain rule, the product rule, or the quotient rule? You've got to start to recognize these things. Let's have a look at them. Here we've got a quotient. Okay, I've got a thing divided by a thing. This one's not a quotient rule. Okay, it's a function in another function. It's a chain rule. Over here, I've got a product. I've got a thing, a function, multiplied by another function, and that's a chain rule there in itself. I've got this pi stuck out here too. Just remember, pi is just a number. Okay, it's 3.14159. So you just treat it like it's 3. It doesn't really matter. So when you're going to do the derivative of pi cos x, you're going to get negative pi sine x. And this is an interesting one too. This is not a quotient rule. Okay, this is a number. So it's not a function that's on the bottom like that one. So here we can just do this one as a half, and then sine x, cos x, and so that's just going to be a product rule. Now I haven't done the answers to these, but if you would like them, I'm happy to do them. But there's 4 really interesting functions, and try and sort out in your own head how you're going to remember which is which. So we've got quotient, chain rule, product rule, product rule. We can differentiate a second time, and this will be denoted by f double dash of x, y double dash, or d squared y dx squared. This one's a little weird, isn't it? It comes from this, doing the derivative of dy dx. So it kind of makes sense why that becomes that. This thing here ought to be in brackets, but they've dropped the brackets over time. So it's a little bit odd. So our second derivative, written this way, is d squared y dx squared. Okay, let's have a look at what happens when we find the second derivatives of these functions. Let's start with sine 2x. We have a chain rule there. So sine is going to become cos, and then I'm going to multiply by the derivative of 2x, which is 2. So it's going to become 2 cos of 2x. When I do the second derivative, cos is going to become negative sine, and again I'm going to multiply by the derivative of this, which is 2, so it'll become negative 4 sine 2x. If that's too fast for you, pause the video and just work them out. This one here is an interesting one. When we do the derivative of e to the negative x, it stays the same, and then I multiply by the derivative of this function, which is minus 1. Bringing it out the front gives me negative e to the negative x. When I do the second derivative, it's all going to stay the same. I'm going to multiply by the derivative of the second function, which is negative 1. It's going to end up being e to the negative x. And this is actually really important in further studies on calculus. E stays the same. After you've differentiated it twice, you're back to what you started with. This is an interesting one too. If I went through 2 more goes, I would be back at positive sine. I get this increased number though going through here. So it goes sine, then cos, then negative sine, then negative cos, then positive sine. So it does kind of eventually return, but not for a while. There are higher derivatives which are important in physics, so we will be doing a whole topic on this, but the first derivative is velocity. So if the base equation is displacement or distance, the first derivative is how is distance or displacement changing with respect to time, so that's velocity. Our second derivative is acceleration, so how fast is velocity changing with respect to time. Our third derivative is called jerk. Fourth derivative is called jounce or snap. Fifth derivative is called crackle. Sixth derivative is called pop, and there are names for the seventh and eighth derivatives as well. Now they're important in physics. I couldn't explain to you what on earth they mean. You'd have to go and look it up yourself. In mathematics, beyond the third derivative, we tend to just use them as an algebraic exercise, nothing more. Let's find the first 6 derivatives of this. Let's have a look. So dy dx is going to be 6x squared. d squared y dx squared will be 12x. d cubed y dx cubed is 12. And then all of these guys are going to be equal to 0. I did mention that earlier in the video. So in each case, the new derivative is finding the slope of the tangent or the instantaneous rate of change of the previous derivative. So how much is the previous derivative changing with respect to x? All right, finish off with the past exam question. Let f of x equal log x minus 5x for x is greater than 0. Part A says find the derivative f dashed of x. So we just do it term by term. Derivative of ln x is 1 on x minus 5. Nice and easy. 2 marks, would you believe? 1 for that and 1 for that. The second derivative now, I'm going to turn that around and make that x to the negative 1. Alright, and again we're just going to go term by term. And this one's going to disappear, so this one's the only one that's really important. And of course the negative comes down, x to the negative 2. And there's our answer. 1 mark in this case. And finally, part C, solve f dashed of x equals f double dashed of x. So we're just going to put those two equal to one another. Put this back onto the denominator. So 1 on x minus 5 equals negative 1 on x squared. Multiply every term by x squared. So multiplying that by x squared gives me x minus 5x squared equals negative 1. And we have a quadratic. This was in the calculator paper, so there's nothing to stop you putting that in the graphics calculator in the polynomial solver. And we get 2 answers, but x is greater than 0, so there's only one answer, and it is 0.558.